The kinetics and thermodynamics of the Sn1 reaction follow directly from the general mechanism. Let me write that out. Carbon with a leaving group and 3 other things attached. Let me continue to track these groups by calling them 1, 2, and 3. In an initial step, that leaving group leaves, taking a pair of electrons with it, breaking the sigma bond, which makes a carbocation intermediate that has the remaining 3 groups attached in a planar arrangement, plus a leaving group. And in a second step, a nucleophile adds to that carbocation intermediate. And that nucleophile can add either to this side of the carbocation or the other side. So 2 products are made, mirror images, that may be identical depending on whether 1, 2, and 3 are all different or not. This is the product that would be made by an Sn2 reaction with inversion. And this is the product that is made by retention of configuration. These are made in essentially equal amounts, so we have a racemic mixture. Now, energetically, these are identical because they're enantiomers. So for the energetics, we can ignore the fact that perhaps this reaction makes a racemic mixture. And remember that we said this would be the slow step, what we call rate determining step. So when we write the rate equation, we need to look at that rate determining step, see how many reactants are involved, and we see that the rate is equal to some rate constant times the concentration of substrate, nothing else. Because there's only 1 reactant in the rate determining step, this is what's called a first order reaction, first order kinetics, which is distinctly different from the Sn2 reaction, second order kinetics. So in terms of the rate of the reactants, substrate and nucleophile, only the substrate appears in the rate equation, and the concentration of that substrate appears in the rate equation. The identity of that substrate, whether it's primary, secondary, or tertiary, also affects the reaction rate, and that would be embedded in this term called the rate constant. That has something to do with the activation energy. So to look at the effect of changes in substrate, we need to look at the energy diagram, which will show us the activation energy. So I've put 2 cases on here. One of them is endogonic, it goes uphill. The other one is exogonic, it goes downhill. Those terms relate to free energy consumed or released. And we can specifically identify that by indicating where the products end up in energy relative to the reactants. In this case, it's uphill, delta G is positive. In this case, it's downhill, delta G is negative. So in terms of the thermodynamics, this reaction may be either uphill or downhill. This may be favorable or unfavorable. The activation energies of the rate determining step speak to the rate of the reaction. And as you see here, this 2-humped energy curve is 2 humps because we have 2 steps, has the large activation energy for the slow step. And that's true whether we have a thermodynamically favorable reaction, as in the right-hand side, or a thermodynamically unfavorable reaction. We're still looking at the rates of the reaction as being determined by the activation energies. Let's take a look at what happens to that activation energy as we change the substrate. The value we're looking at now is the activation energy as shown here. And you'll recall that we said that the rate of this reaction is sensitive to both the leaving group and the structure of the alkyl group. More alkyl substituents increases the rate of the reaction. Better leaving group increases the rate of the reaction. That would be reflected in the energy diagram. Better leaving group or greater alkyl substitution would lower that activation energy, and the reaction is faster. So those changes in leaving group and alkyl group substitution affect the activation energy in the first step, and this will be a lower hump. You'll notice that I've also implied that those changes will affect the stability of the carbocation intermediate, and we can talk about that another time. But it's not the stability of the carbocation intermediate that's important, is it? It's the stability of the transition state that's important, because that's what affects the activation energy. And as we go to less alkyl substitution, or a poor leaving group, the activation energy will be higher. So worse leaving group, less alkyl substitution on that carbon that bears the leaving group. Both give rise to increased activation energy, slower rates, in the rate determining step, which is this first step. And that summarizes what we need to know about the thermodynamics and the kinetics. In terms of thermodynamics, we're looking at the overall process, not one step or the other, but the overall process, and comparing what we start with to what we end up with. For kinetics, we're focusing only on the slow step, the rate determining step, and looking at what changes in the rate we see when we change aspects of the substrate. More or less alkyl substitution, better or worse leaving group. All summarized in the energy diagram. Very powerful.